So last class, when we left off, we were doing something called a 2-3-4 tree. It was another method for searching. It was quicker searching. We had to do a little extra work up front, but we created this AVL, Adelson, no, that was the rotating left and right. That's right. Adelson-Velsky-Landis, binary, -1, balance factors. Whew. Hope you're taking good notes down the stretch here. This final's got a lot of good stuff on. But we were doing something called a 2-3-4 tree. And we were filling it up. And when we looked at the 2-3-4 tree, we talked about we could have as many as 3 items on the first level. And then on the second level, we could have 12 more items for a grand total of 15. Because our node size, we stored 3 data items. We had 4 pointers coming out. And out of this one, each one of these, we had 4. So here's 4 more 3s and 4 more 3s. And, we started to pick up a pattern of this was 3. This guy was 4 times 3, which gave me the 15. Then we had 16 times 3, and we kept adding it. And we kept adding more and more numbers. So I had 3 items here, which gave me a grand total of 3. I had 12 new items, which gave me a grand total of 15. We decided how many items on this next row? And we ended up going with, this was 4 to the 0 times 3. This level was 4 to the first power times 3. The next level was 4 to the second power times 3, because I had 4 and then 16. And so, yeah, this was the old 48 for the level, 63 for the total. We started coming up with the total actually was 2 to the n minus 1 power minus 1, something along those lines. We were bringing our pre-calc into play, but we were able to store as many as 63 items in a tree of height 2, of height 3. So we were able to cut our search time down quite a bit. All right, so let's take a look at these numbers. And I'm going to give you 2 minutes, 3 minutes. Build a 2-3-4 tree with the numbers that you see above. I will pause the video as long as somebody reminds me to start it. So I had 53 by itself. I then added 27 to the 53. And remember, we talked about the insertion part, how I'd have to move the 53 over. Then I added the 75. I went to add 25 and it blew up. So the 25 is over here on this left side. So 25 and 27 are going to now come down. So 53 is all by its lonesome. 25 and 27 and 75. The other day we were drawing these with blanks as well to show that when the 27 left and the 75 left, the 53 actually had to jump to the left. So I had 53, 27, 75, 25. I now add 70. So 70 could go over there on the right side. Trying to make this look pretty. Not too bad. 41, that's going to sneak over here onto the left side because it's less than 53. Goes into that node. get them in order. 38 now comes to the left, but 38 is going to blow this guy up. 27 is the middle term, so 27 would leave. I have 27 and 53. To the left of the 27 is just a 25. Between the 27 and 53 is the 38 and the 41. And to the right of the 53 is 70 and 75. So I just added 38. If I add 16, it's going down with the 25. If I added 59, it's going to fit right in there. That guy's full. And it looks like if I add 28, it's going to go there. Hopefully I didn't mess anything up. And I did. 28 doesn't go there, does it? Where does the 28 go?
Down by the 38.
Yeah, it goes in here, which means this guy blows up. And what's my last row look like? 27, 41, 53.
So wouldn't the 59 go to the left of 70?
Yeah, why in the heck is the 59 there? You folks sit there and don't say anything till it's too late. You're killing me. All right, so let's back up. I'm at this point. I just added 16. I now add 59, which is greater than 53, so it's going to go in here. Sorry about that. I add 28, which is going to go in here. Does that look better? Less than 27, between 27 and 53, greater than 53. Now, a number that would blow it up. Something between 27 and 53 would go in here. I'd have to move one up. A number greater than 53 would have to move one up. I would then be taking advantage of all 4 pointers. So it allows me to keep adding numbers for quite a while until I then have to go to a new level. Questions? Now, somebody got the idea of, what if I took this and what if there was a way to represent this tree as a binary tree? And there is. It's called a red-black tree, and that's what we're going to take a look at today. A red-black tree. The final result of this is going to be what we're going to do first, because I want you to take a look at what the whole would be. Then we're going to do a side-by-side building of the red-black tree with what we just did with 2, 3, 4 to understand how it's built. But as I said, there's probably a reason why a red-black tree is needed instead of here. Now, what's the rules of a red-black tree? Well, a couple of rules. The first one is siblings are connected by a red pointer. Siblings are a red pointer, okay? We will never have 2 consecutive red pointers. Otherwise, it's connected by black. So I'm going to start at the top. I'm going to get a number. Pick a number, 27 or 53, doesn't matter. Pick one of them. Good.
53.
53.
27.
So here's the 53. And I'm basically building a binary tree out of this. All right. Now, 27 is its sibling. So where would the 27 go? Well, if I'm building a binary search tree, where does the 27 go? To the
Left.
to the left. So over here is going to be 27. And I'm going to connect it with the red because all siblings are connected with red. All right. Now I have children of 27. I have two of them, 16 and 25. Pick one of those. Doesn't matter which one.
16.
16. So if I draw the 16 on the next level, I know that this is not a sibling, but a child. So I'm going to connect that with black. And now I'm going to draw the 25, which should be to the right of the 16. And since it's a sibling, I'm going to connect it with red. So 27 and 53 are siblings. 16 and 25 are siblings. 16 is a child of 27. Next node is the 27. I'm going to take a look at 28, 38, and 41. Again, this isn't the only solution, but this is a solution. So I'm going to ask you again, pick a number out of that 28, 38, and 41.
41.
The 41, okay? So I know the 41 is going to be sitting over here to the right. All right. It is a child of 27, so it's connected with black. My other two numbers in there are 28 and 38. 28 and 38 are both children. I think since there's 3 in the node, we have to go with the middle one. So instead of the 41, I'm going to say, let's go back, and it's going to be 38. 38 has a sibling, 38. It has a sibling of 28. It has a sibling of 41. Again, don't panic yet. This is just an example of what the output would look like for a red-black binary tree that has the same representation as what we learned last Thursday, the 2, 3, 4 tree. 53, I'm going to come over and I'm going to put 70. It's a child, so it's connected with black. It has 59 and 75 as siblings, and these are connected with red. Now, what are some things that you notice here? We start to talk about this from our example. I'm making a couple of notes, and I'm going to say that I see no 2 consecutive reds. We almost had some kind of mess going here, but again, I'm just showing you what the final is. As we build it, you'll see how this makes a little more sense. Other things you notice. Every path has the same number of that wasn't a dramatic pause. That was a pause for you to give me every path has the same number of, starts with the letter B. Good. I just put it, black links. There are no consecutive reds. We also notice that every path has the same number of black links. So that's my whole, that's my final, that's what I want to end up with. So in order to learn how to build a red-black binary tree, I'm going to go and I'm going to mirror how I built my 2, 3, 4 tree, because they are in fact directly related. Ta-da. Okay, so let's see. I'm going to start with the first number. Wish me luck. Here we go. I'm going to start with 53. Okay, yay for 53. I'm now gonna, let's see, I added 27. I added 27. And when I added 27, I added it. And when I added it, it was a what? A sibling. And I know siblings are red. I added 75. It's greater than 53. It's a sibling, so it's red. The next number, let's see, I did 53, 27. The next number I want to add is 25. And when I add the 25, it's going to come down to less than 27. And let's see, when I was adding things, you know, I was adding them as reds and so and so and so and so. But when I added the 25, I would have gotten 2 consecutive reds. And what happened when I added the 25 over here? Well, it became a child, so it has to be blowing this up. When I added 25, it blew this up. When I add 25 as a red, it's going to blow this up. So when I added the 25, I ended up getting 53, 25, 27, and 75. So when this became a red, so let's see, I now had something that looked like 53. I had 27. I had 25. Over here, I had 75. When I added this as a red, I went, uh-oh, that's no good. I blew it up. These two now became siblings. 53 stayed. 25 and 27 went here. 75 went there. These two became black. Still have those rules of each path has the same number of blacks. So I'm doing some things right there. The next number after 25 is 70. 70 is going to get added. It's to the left. It's a sibling. So it gets red, and I start looking up, and I see I'm still okay. The next number was 41. 41 goes to the right here. I add it as a red. It's just a sibling, and I'm looking pretty good here. I have my 53, my 27, my 25, my 41, my 70, 75. I would add 38. I'm going to add 38. And I know it's going to be a problem because 38 is going to go here, and I'm going to have 2 consecutive reds, which means there's a problem. So I needed to blow it up this way. So let's see, I have 53. Still have 27 here. I have 75. I have, oops, I shouldn't have done that yet. I have 70. I had 25. I had 41. And the new number I just added was 38. Remember, when I put 38 here, that would give me that. So let's see what happens when I added 38. I would have had 2 reds in a row. When I added 38 here, 27 went up. So the 27 now becomes a sibling. So, you know, my logic is when I get those 2 reds, this became a sibling of 27, and 53 are now siblings. Over on the right side, over here on the right side, to the right of 53, I still have a black. to that and a red because these two are siblings. So I said I shouldn't have put that in there so quick. 27 had a child of 25. 27 had a child of 25. 27 had a child of 41. And 41 and 38 were siblings. Every path has the exact same number of blacks, 1, 1, and 1. Just added 38. I'd now like to add 16. 16 is going to go over here. It is going to be a sibling of 25. Became a sibling of 25. I'm going to add 59. 59 is greater than, less than, less than. And when I added 59, I had another sibling. When I add 59, it's going to go here. And what happens? It's a sibling. Yeah, you don't even want to know what happens now. Any suggestions what happens now? My rules were, my final solution, I don't know where I wrote it. No 2 consecutive reds. So if I added 59, that would actually give me 2 consecutive reds. What would I have to do in this case with the 2 consecutive reds?
Move something up.
Tell me what it is. It's RR, not railroad. Adelson-Valsky.
Can you just swap 70 and 75? Like where they're at?
How about a right rotation?
Oh, yeah.
Move the 75 up. 59 is to the left would be red. 70 to the right to the 75 would be red. So the siblings would all be red. I would not have 2 reds in a row. Every path has the same number of black. So it would now need to become something that looks like 53, 27, 70, 25, 41, 59, 75, and 16. Let's see, these two are siblings, I know that. I know these guys are siblings. I know that 16 and 25, we have some siblings going on there. I forgot to write the 38. These guys were still siblings, and this was a black, this was a black, and that was a black. And there it is, a red-black tree. What do you think about that?
It's
Tough
weird.
crowd. Yeah, it is weird. I was gonna say tough crowd, folks, tough crowd. Another one?
Probably.
Okay, so I want you to do another red-black tree. This time, you can try it red-black. I don't know all the rules. So I think if it was me, I would do the 2, 3, 4 tree beside it and see what I come up with. 50, 25, 75, 37. Just throwing some numbers out. 68, 40, 9, 42. Let's just do a couple more. 70, 76. Create a red-black tree. Every path has to have only one black. No two reds in a row. Look at that, I have 3 numbers done already. What do you think of that? Partial credit. Final exam. Tuesday, May 11th, from 9 to 11 a.m. Tuesday, May 11th, 9 to 11 a.m.
Hey, Professor.
Hey, what?
So I have jury duty on May 11th.
Okay. I will be giving a final Monday night before that from 6 to 8. Or the Friday before that, that first week of finals. Finals start on a Thursday. I don't have any Thursday, but I have one on Friday. So I will give folks the option to come to either one of those two if they want to take it early. I'll
What
put
day is that again?
Either Friday, May 7th from 10 to 12
PM or AM?
a.m.
Okay.
Staying up till midnight. Monday, May 10th from 6 to 8 p.m. All right, let's see. If I add 37, it blows this up. And I know my new one is going to be 50, 25, 37.
What were the times again for May 10th?
May 10th was 6 to 8 p.m.
Okay, thank you.
If I was over here, I had the 50, I have the 25, I have the 75. And when I went to add 37, I would have gotten 2 reds in a row. So yeah, it blows up. So the 37 is still going to be here. And when it blew, because I was going to add a red here, and when it blew up, 27 stayed that sibling, but these 2 guys turned to black. When I got those 2 reds in a row, adding 37, it turned to black. The next number I would add is 68. See, greater than 50, less than 75. There goes 68. And I don't know why I drew that, because it's a sibling. 68. If I add 40, less than 40 is going down here, and that gives me 2 reds in a row. So let's see, a moment ago, I just added 68, right? Now I want to add 40, and the 40 is going to go in with this guy. So now I'm going to have 50. I'm going to have 25, 37, and 48. Over here will be 68 and 75. That's my current situation. And when I added 40, I got 2 reds in a row. But this time, let's see. This time it looks like they're both right reds. So the 2 reds in a row, maybe that's a pattern. What if I had 2 lefts in a row? What do you think I have to do if I have 2 rights in a row? Because I just added that as a sibling.
Left
Where did you get
rotation.
48 from?
Yeah, I'm thinking left rotation. So there's the 50. This now becomes 37, 75. Over here's 25, 40, and 68. So you better learn a little bit of everything to be able to do everything.
So couldn't this rotation be avoided if you always put the middle term in whenever you're blowing things up?
when you're building it here?
No, whenever you're doing the red black tree. So if you would have put in 37 where 25 is, and then you would have had 25, and then whenever you had 40.
How would you have known how did you know the next number was gonna be 40? The next number could have been
Well-
23,
Oh, that's true.
which would have fit nice, yeah.
Okay.
All right, we just added 68, we added 40. Next thing I'd like to add is a 9. Oh, and when I add a 9 here, maybe my logic of rotation didn't work, because when I add a 9 here, what's gonna happen? Well, this is full. So maybe when I add the 9, I do have 2 lefts, but I also have the right. So now it needs to blow up. So let's see, my next graph is going to be 50, 37, 75, 25, 40, 68. Over here's a 9. What happens when I added a 9 here? The 37 went up, and I had 3750. I had, let's see, 9 and 25. I have 48. I have 68 and 75. So up here's where I had my second red in a row. And it blew up, and it became, this red stayed. This became a black. That became a red. This became a black. Again, this became a red when I brought the 25 in. Above it, these two became black, and that became a red. The link between 25 and 37 black, 37, 40 black, 37 up to 50 was a red. Okay, so I'm just going by what I had. And when this became a red, these two became blacks. This became a red. This became a black, and this became a red. Somebody said, please don't make me program this. Please, I have my node, and I would just be kind of curious what y'all thought. We just added 9. I don't know if we need to add 42 and 70, and 42 would come in and go here, fit nice. 70 would come in, but this 70 would be over to there kind of deal, and I might have to make something go crazy here. But what kind of struct would you have for this bad boy? If I was going to build a struct, what would I build? I know this, num1, num2, num3. Would you do that? Would you do a vector? Would you do an array to hold the values? What else might go in your struct? Well, I know there's going to be 4 pointers, right?
It's like
Somebody say it. Huh?
left pointer, a left middle, a right middle.
Right.
Left middle, right middle, right. Anything else in the pointer? Or in struct, excuse me. Well, what do I also know about the pointers? Each pointer has to have its own unique color. So I might have some chars that would be L pointer color. So I know if it's red or black. LM pointer color. RM pointer color and R pointer color. Jeez. Anybody thinking they want to code this? No. Matthew says not a problem, piece of cake. What numbers do I have back over here that I might want to add? A 42, which is less than, greater than, greater than. And when I add that, it became, why do I not have a 40 over here? Or is this a 48? This is supposed to be a 40. Why is that a 48? I have 40s. 42. Yeah, that would fit right in there as a sibling, so I add it. I don't have the two reds in a row. Everything looks pretty good. So 42 is now in here. 48, I'm sorry, 70 is the next number. 70 would come in and land 68, da 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 da. And now all of a sudden 70 is going here. I shouldn't have drawn that because when it comes in, it's a red, right? But now I have two reds in a row. And wow, what would I have to do here? This is kind of bizarre. Here's a left, here's a right. I'd like to end up with 70 having a left child of 68 and a right child of 75. How would I get 70 up there? I'd have to do a Adelson-Belsky. A left-right rotation. Because I just added 70, which fits in this node. And in order to keep my binary tree the way I want it, I'm going to have to rotate 70 up with 68 down. And then I'd have to rotate 70 up so that 75 goes down. Ooh. And then, of course, when I added the 76 finally, it blows all of this up and we would go from there. The thing about this I like is we're doing something new, building on the 2, 3, 4 tree and building on Adelson-Belsky as well. Easy? No, not at all. Doable? Yeah, yeah. Questions? Okay. The last thing we're going to talk about, something called a B tree. A B tree is a tree where, you know, I have something, it's what we call an order M ADT. Okay, the order M abstract data type, where, and again, just like we've been doing with the 2, 4, 3 trees, you can have M-1 pieces of data, which means you would then have M pointers. Okay. So we started looking at some examples here, and let's go back to our good old binary tree. Binary tree would be an M equal to 2 kind of deal. All right. And when I'm at a height of 1, how many values are stored in my traditional binary tree? Just 1, right? When I had a height 2, how many values were stored in my binary tree? 1 and then 2, total of 3. When I went to 3, what did I have? 1, 2, 4, Then I added 8 more. So a 3 and then plus 4 is 7. And then when I went to the 4th level, I could get 15. And, you know, even if I wanted to go to the 5th level, crazy. 5th level, I'd add another 6. 31 values could be stored in a binary tree of height 5. We just took a look at 2, 3, 4 trees. In this case, M is 4. So on my height of was 3. We just looked at that a minute ago. The next level was 15. Right, we were looking at that up here. The total values that could be stored. By level 3, I can store 63 values. So if I have a lot of values, is it better to do all of that extra work for a B tree of size 4? Somebody have a number for the next one? So think shortcuts. Think shortcuts. Think patterns. Think somebody have it?
Hang on.
Does it start with a 2?
255.
255. What do you think the next one is?
1023.
Yeah, now we're getting the pattern, right? Give me a formula. Instead of 6, what if I said n?
N times 4 plus 3.
N times 4. So wait, no, wait. 5 times 4 is 20 plus 3. That only gives me the 23.
Oh, then I have no idea how I got it then. I have a completely different pattern.
And that's possible.
You
But I
take
think there's-
the
That was the pattern for m equals 4. Like going from each m value,
Okay,
m equals 4 down
yeah,
that
the previous
list.
like 255 times 4 plus 3 is 1023.
so
That's what I was doing too.
n would be what? 4 to the,
I
4 to
don't
the
know.
n minus 1.
4 to the nth power minus
Right.
1. What was this one? How'd I get the 31? 2 to the height power, 2 to the 5th power minus, this is 2 to the n power minus 1.
So m to the n minus 1.
Yeah, so my generic formula should be m to the n minus 1. So if I come up here, I can fill out this row if I'm storing 10 values in a node. I don't think I want to do that, unless there's easier ways to do it than what we've been looking at. I know my first level is 9. My second level is m to the n power minus 1. 10 squared minus 1. 10 cubed minus 1. Ooh. 10 to the 4th power minus 1. 9,999 values within a height of 4. And again, we liked our m to the n minus 1 guy. Yeah, we liked it. Okay, so we could take 2, 3, 4 trees, binary trees, to a new level called a B tree. And it would be amazing number of values to be stored. Are we gonna actually draw the tree? No, we're not gonna draw the tree. Questions? Questions? We still have 25 minutes. I'm not starting anything new.
This is weird.
It's weird. So I know all of you are great students and you've already started making a list of what's on this next test. And you have great notes and you're ready to roll. And, you know, I'm looking at what did we start with? We started with sorting. Sound about right? 3 different sorts: selection, exchange, insertion sorts. We then went to selection, exchange, insertion sort. We then went to heaps. Give me some great words that we learned with heaps.
Heapify.
Heapify, that was a great one. 2 more.
I was thinking
Percolate.
max and min, but
No, these were actually functions.
Push heap, pop heap.
No,
Percolate up,
Percolate up and
percolate down,
percolate down.
percolate
Yeah.
up, percolate down.
percolate up and percolate down. Because remember, a heap wasn't a binary search tree. For a heap, it had to be, what did it have to be for a heap? It had to be complete. And the parent had to be larger than the child. That's it. Wasn't necessarily about, we weren't searching a heap. We were using this for sorting purposes. Once it became a heap, because we did the heapify, we took the largest and moved it at the end to help us with sorting. We liked heaps. Still in this whole sorting idea, we then did the quicksort. Tell me about quicksort.
Oh man, what's that?
If you give me one word, it starts with a P and don't say percolate up.
Pivot, right?
Pivot, yeah. In the quicksort, you had a pivot. You moved through the rest of the list. Items left then got grouped together, items greater than got grouped together, and then we recursively went through the quicksort. Another sort, merge sort. There were 2 of them. Binary and natural. I kept creating 2 lists and going from there. The erratic sort. We beat the heck out of sorting in chapter 13. Sound about right? Staying with the idea of trees, we then jumped to chapter 15. This was 13. Lots of sorting. 15, what did we do so far? We liked it. Huffman codes. Yeah, I like Tuffman codes. Thought that was kind of cool. AVL. Adelson, Belsky, Landis. That had a balance factor. What were my balance factors? In order for me to have a balanced tree, I needed what balance factors?
-1, 0, and 1.
Right, -1, 0, and 1. That's when I did a rotation left, a rotation right, a left, right, right and left. I did a whole bunch of different things with that. Not a real fan of that. But that was tree balancing. We wanted to keep it balanced. And now finally, some more work with trees, because this chapter was sorting. This chapter is trees. We did 2, 3, 4. We did red, black. And we did a quick mention of B trees. All sound familiar? No.
Yes.
No, we're getting some no's, some some yeses. And so that's, where are you as far as getting ready for the final? We have one more chapter, chapter 16, and we're going to learn about graphs, which is going to take trees. And instead of looking at our trees nice and vertically, where we start at the top and work our way down, we're going to look at graphs, not in the traditional college algebra sense, but graphs that are all over the place. Like if you looked at all the cities on a map, and if you looked at airports and flights that went from one airport to the next back in not long after 1930, and you could see, that's what a graph is going to start to look like. And yeah, I did have a course in graph theory a long time ago. We have time. Any quick questions on any of these? You're going to say, oh, can we do one of those real quick? Somebody else showed up? No, we're still missing Mark and Yug.
No, I can.
Who's I? Mark?
Mark, yep.
And somebody left early. Who snuck out? Son of a gun. Any questions? Going once, going twice.